Hi and welcome. Let's start with the start of our show acids and bases. According to Bronst and Lowry, acids are the generous dancers. They are proton donors, always ready to give away an H plus ion. Bases, on the other hand, are the eager receivers, proton acceptors, who are happy to take what acids offer. Think of it like a dance partnership where one leads and the other follows. When hydrogen chloride meets water, hydrogen chloride said, "Here, take my proton," and water graciously accepts it, becoming hydronium ion, also known as oxonium ion. This creates what we call conjugate pairs. They are like dance partners who are forever linked by this single proton exchange. Now, here is something fascinating. Water doesn't just sit there quietly. Even pure water has its own little dance going on. Water molecules are constantly bumping into each other, and occasionally one steals a proton from another. This creates our hydronium ion and hydroxide ion. The equilibrium constant for this dance is Kw, and it equals 1 times 10 to the negative 14th at 25 degrees Celsius. In pure water, the concentrations are perfectly balanced, like synchronized swimmers, both at 1 times 10 to the negative 7th molar. Not all acids are created equal. Some are generous proton donors, others are more stingy. We measure this generosity with the acid dissociation constant, Ka. Picture this. A strong acid is like someone who can't hold on to their money. They give away protons completely. A large Ka means the acid dissociates almost entirely. A weak acid, however, is like someone who's reluctant to spend. They hold on to most of their protons, creating an equilibrium situation. Let me introduce you to the VIP acids, the strong ones. There are only 6 common strong acids, and I like to remember them as the big 6. We have the hydrogen chloride, the hydrobromic acid, the hydroiodic acid. These are the halogen trio, plus the nitric acid, sulfuric acid, and perchloric acid. These guys don't mess around. They ionize completely in water. Weak acids, like acetic acid in vinegar, are more polite. They only partially dissociate, setting up an equilibrium dance between the molecular acid and its ions. Bases have their own dissociation constant called Kb. Here is a beautiful relationship in chemistry. For any conjugate acid-base pair, Ka times Kb always equals Kw. It's like a cosmic balance. If you know how good an acid is at giving up protons, you automatically know how good its conjugate base is at accepting them. Nature loves this kind of symmetry. Now let's talk about the pH scale, chemistry's way of making the incredibly tiny concentrations of hydronium ion more manageable. pH is simply the negative log of the hydronium concentration. This gives us a scale from 0 to 14, where 7 is perfectly neutral. Here is the cool part. Each pH unit represents a 10-fold change in acidity. So pH 3 is 10 times more acidic than pH 4 and 100 times more acidic than pH 5. It's logarithmic magic. For strong acids, life is simple because they completely dissociate. If I have 0.01 mole of hydrogen chloride, I know that all of it becomes hydronium. So my hydronium concentrations is 0.01 mole. Taking the negative log gives me pH equal 2. Easy as pie, strong acids are the straightforward friends of the chemistry world. Weak acids require a bit more finesse. This is where we use the ice table method. Initial concentrations, change in concentrations, and equilibrium concentrations. It's like solving a puzzle where we know the starting point and the rules, Ka, and we need to figure out where everything ends up. The math might look intimidating, but it's just systematic bookkeeping. Some acids are like generous hosts with multiple gifts to give. They are called polyprotic acids. Sulfuric acid can donate 2 protons. Phosphoric acid can donate 3. But here is the interesting thing. They don't give them all up at once. It's like opening presents one at a time, where each subsequent proton is harder to remove than the last. Usually the first dissociation dominates the pH calculations. When salts dissolve in water, they don't always mind their own business. Some of their ions react with water, affecting the pH. It's like having house guests who rearrange your furniture. If the salt comes from a strong acid and strong base, it's neutral, well-behaved guest. But if it comes from a weak acid and strong base, the conjugate base makes the solution basic. Chemistry has rules even for these secondary interactions. Indicators are chemistry's mood rings. They are weak acids themselves, but their claim to fame is that their molecular form and ionic form have dramatically different colors. As pH changes, the equilibrium between these forms shifts, creating a color change. The transition happens over about 2 pH units, centered around the indicator pKa. It's visual chemistry at its finest. Acid-base chemistry isn't just academic, it's everywhere. Your blood maintains a pH between 7.35 and 7.45, and even tiny deviations can be life-threatening. Your stomach cranks out acid with a pH around 1 to 2 to digest food. In industry, we use acid-base chemistry for water treatment, food preservation, and countless manufacturing processes. It's the invisible force keeping our world running smoothly. Now, when tackling acid-base problems, think like a detective. First, identify your suspect. Is it a strong or weak acid or base? Then write the equilibrium expression. This is your evidence. Set up your ice table if dealing with weak species. And don't forget to check if approximations are valid. Finally, always ask yourself, does this answer make sense? A pH of 5 for a household chemical should raise red flags. So this is all for this lecture. See you in the next one.